Alright guys, welcome back. So we're going to go over worksheet 4, which is going to be naming our alkanes. So let's go ahead and get started with our first substituents up here. So go ahead and pause the video and tell me exactly what this part means. Alright, so that part essentially means other stuff, right? It's just a way of denoting that there's more to this molecule that we're not mentioning. Reason being, in this case, we just want to focus on our substituents. So let's go ahead and label all of these. So this is just going to be memorization for most of these. So this is going to be our methyl group. So the way we identify our substituents is that they generally end with this YL. So they look like that. So this is a methyl group. This one right here is going to be our isopropyl group. This one up here is going to be our isobutyl group. This next one is going to be sec-butyl. And finally, this one's going to be our ethyl group. So remember, whenever we're naming our alkanes for these this first one and this last one, these kind of look like methane, and this one looks like ethane. Reason being is that they use the exact same naming convention, right? So what we'll do, instead of saying methane or ethane, we'll say methyl or ethyl. And you can kind of see how this goes. So propane becomes propyl, butane becomes butyl. And you kind of see that over here. So we have butyl here, right? The reason why it's called butyl is because we have 1, 2, 3, 4 carbons. We look at this one, 1, 2, 3, 4 carbons. So a key thing to note that a lot of students get tripped up with is that they'll count this carbon here. Let's say there's a carbon already connected here. Let's draw another molecule. And what people will say is that these are all the carbons in the substituent. And that is not true, because this carbon here is part of the chain, right? This blue portion is the substituent. It is just being connected to the main chain through this bond here. It's not going to show up. Through this bond here. Connects the substituent to the main chain. So this bond connects to the main chain. This bond connects to the main chain because we have a CH3 here, right? Our methyl group. And that's the same for all of them. This carbon does not count. That's just the bond connecting to the main group. Next, we're just going to name all the following compounds. So this first one, the very first rule when it comes to naming our compounds is we're going to identify the longest chain. So let's go ahead and just find our longest chain. And this is going to be a little bit of trial and error. You can kind of see which one's going to be the longest chain, but in a lot of them, it won't be as clear. So let's go ahead and just start from here. 1, 2, 3, 4. So I could either go the way I went here, or I could go up. Either way, they give me the same number. So at this point, just pick a path and go with it, right? So I'm gonna make that a little bit neater on the bottom. So I have 4 carbons here. What group is going to be 4 carbons long? That's going to be our butanes. So we know our parent name is butane, something butane. Now we're going to go find our substituents. So we only have one substituent here, which is that, what is it? Methyl group. And now we need to figure out how we're going to number this. So we can either number it the way I show here, or instead of starting from this carbon here, we can now instead start from this carbon here. Right? So we have 2 ways of naming this compound. And which one are we going to pick? We're going to pick the one that gives us the smaller substituent number. So if I were to go with this red line, this red path of numbers, I would get methyl at carbon 3. But if I were to do it the other way, with the black, I would get methyl at carbon 2. So we want to go with the substituent, the numbering scheme that gives us the smallest substituent count. And this is going to be the most important rule when we're naming alkanes, is we want to keep the substituents as low as we can. or not the substituent, sorry, the number that is associated with the substituents as low as we can. So this is going to be 2-methyl. This methyl group is on carbon 2. So now all we do is our next step is going to be to alphabetize everything, right? We're going to take all of our substituents and we're going to alphabetize them and then put it all together. So in this case, we only have one substituent, so we don't have to do any alphabetizing. When we get to our last substituent, we just write the parent right next to it. If we were to have multiple, which we'll see in a little bit, we would have to use dashes to separate them. Going back up here, just a little reminder. So remember, we use the first letter to alphabetize, right? We know how to do that. Some edge cases, isopropyl, you use the I to alphabetize. Isobutyl, same idea. But when we get to these, we use the B. We don't use the S in sec-butyl. I don't know why, it's just like that. So the B is used. Isopropyl and one other substituent that you don't need to know. Actually, forget I said that. Isopropyl is the only one that you need to know that iso is used for alphabetizing. Right. The I. So just remember that. I and isopropyl, you alphabetize. Everything else, you kind of use, I guess, the main chain kind of thing. Because think about this like another substituent. The sec is saying you're kind of connecting to the second carbon, right? That's what it's kind of saying. It's like a modifier of some sort, right? So you use the main chain butyl because we have 4 carbons here, right? And then everything else is good. All right, so this first molecule is going to be 2-methylbutane. Pretty simple, right? Not too bad. So we have our next molecule. And I'm just going to pick a side to start numbering. And I'm just going to start from here. 3, 4, 5, and I can go up or down. And just by inspection, looks like this top one is going to be longer. And there we go. We have a 9-carbon chain. So what does that tell us? What is our 9-carbon chains called? Nonane. This is a nonane molecule. Now we're just going to go through and identify all of our substituents. So I have a substituent here. And this is a methyl. Let's go down here. What is this one? It's a sec-butyl. And this last one is another methyl. Actually, we have 2 methyls right over there. All right, so now we're in a little bit of predicament, right? So we need to find the way, so we can number this 2 ways, right? We can start from the way we did, or we can start the other way. So now that we see, if we start on either side, we both hit a substituent at our, I'm doing air quotes right now, carbon 2, right? When we hit substituents, let's say we have the same substituents at the same carbon number, the next thing we would do is we would look for the one that is the next closest from that first one, right? Okay, that doesn't make much sense the way I said it, right? But let's say I had this molecule, right? Let's say I had a chain that goes up like this, right? So I'm between these two, right? I can number it going from, let's get my laser point. I can number it going from here, this way, the way in red, or I can number it from this way, going this way, the way I have it in blue, right? Both of them have a substituent at carbon 2 in their respective paths. The way I would break the tie is look at which path has the next substituent appearing first, right? So in this case, in the red path, my second substituent only appears at carbon 5. Looking at this other side, if I went the blue path, my second substituent occurs at carbon 4. So 4 beats 5, I would take the blue path. But now you're saying, well, we don't have that, right? Both of them end up at carbon 5, right? Both ways that I go ends up at carbon 5. So in this case, the thing that breaks the tie is that the fact that there's 2 methyls here. So the fact that there's 2 methyls here says that we're going to go from this side. So we're going to take the blue path. So since we have two methyls here and we have one methyl over here, how many methyls do we have? We have 3 methyls. Good job, guys. That is math. So we have 3 methyls, and when we name our molecules, we also add a little prefix to them, right? And what is that going to be? So if we have 3 methyls, this means it's trimethyl, right? So now we're just going to name it. So we have all of our substituents. I'm just going to write the carbon number on this one. And remember how we name substituents on a chain? We name them at every single carbon that they appear in the order that they appear. So in this case, we have 2 methyls on carbon 2. So we write it as 2, 2, because we write it for each time it appears, and then 8 trimethyl, and that's our substituent, right? So we have these 3 pieces. We have 2,2,8 trimethyl, 5-sec-butyl, and nonane. Now, when we put it all together, we alphabetize. So remember, we don't go based off of the S in sec-butyl. We go off of the B. And in this case, in trimethyl, we don't go off of the T in trimethyl. We go off of the M, right? These are like modifiers. We're going to ignore the modifiers. So what comes before? What comes first in this? B. Good job, guys. So this is 5-sec-butyl. 5-sec-butyl. My handwriting's not the best here. The next is 2,2,8 trimethyl. And then finally, our parent chain, nonane. And there you go. That's how you name that one. All right, let's go ahead and do that. And looking at this, we kind of know we can start to combine all of our rules into one go. So let's see here. Let's go ahead, and I can number this like this, starting from here: 1, 2, 3, 4, 5, 6, 7. All right, sounds good, right? Let's see here. There's multiple ways. This does look a little suspicious, so let me go ahead and do it another way. 1, 2, 3, 4, 5, and then I can continue this way and get to 7, or I can go up here, 6, 7, 8. Oh, I have a longer chain. So this is not my longest chain. It's actually this one that goes up. So be careful. There might be a longer chain. From just looking at it, it looked like it was a pretty simple one, a pretty simple heptane. But no, this is a octane molecule. So I'm going to erase all of my red numbers. And now we're just going to be doing what we did before. And that's going to be naming our substituents. So we have this group here. We have 2 carbons. What is that called? Ethyl. And then we have our little humble methyl. Did we name this the correct way to minimize our substituent numbers? We did not. So let's fix that. 1, 2, 3, 4, 5, 6, 7, 8. Methyl will be at 2, so 2-methyl. And ethyl will be at 4, 4-ethyl. And then we're going to go ahead and make sure that all of our alphabets are the same. So E comes before M. 4-ethyl. Was it 2? 2-methyl. Octane. And that is our molecule right there. Pretty simple, not too bad. All right, next one. Now we have some rings going on. So first, we identify what the ring is. What is this ring? That's right, it's a cyclohexane. So notice we have 1, 2, 3, 4, 5, 6. If this was not cyclic, if this was acyclic, what would that be? It would be hexane, but it is cyclic. So what did we do? We added the cyclo. That's all we did. Everything else is the same with the naming. Or not everything, but If I had this, what is this called? right? We have 1, 2, 3, 4, 5 carbons. That makes it a pentane. So this one is cyclopentane. And this one, what is this one? We have 3 carbons, cyclopropane. We have this one, what is this one called? Cyclobutane, and more. And you get the idea. So we have cyclohexane here. Go ahead and name all of our substituents. So we have a methane, or a methyl, sorry, another methyl, and we have an ethyl. Ethyl and a methyl. How are we going to name this one? So, in this case, there's nothing, like let's say I started off with this one to be carbon 1. I could go down to 3, my next substituent is at 3. Or I could go up to 3, my next one is at 3. Right? So that doesn't, if I started at that methyl, I don't really know which way I would go. They're both equal paths. If I started at this methyl, same deal. If I started at this ethyl, same deal. So, we don't really have a good first path to go from. So what do? So we now go off of alphabeticity, right? So we have 2 methyls and we have 1 ethyl. Which one beats out when you alphabetize them? It's ethyl. So this ethyl will be first. This is carbon 1. And then we go around in the circle. So in this case, both of them are equally spaced apart. So just pick a direction. It doesn't matter. And there you go. That's all you do. So now we can do everything that we've been doing. So we have 1 ethyl, and then 3, 5, because it shows up at carbon 3 and 5, dimethyl, and here's the most important part. People always forget to write cyclo. It seems simple until you do it. Remember, if you have a cyclic molecule, it has to say cyclo. Well, actually, asterisk. We'll see that in a minute, but if you mean to say cyclohexane, make sure you write the cyclo. And all right, so this one, pretty simple, guys. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right, pretty easy, guys. This is going to be 4 isopropyl monodegrade. Cool. This is kind of a joke one, so you don't, the same ideas are still there. Right? This is our parent chain here, and then here's our isopropyl group right here at carbon 4. If we did it the other way, the substituent number would be too high, and that's not good. You won't see ones that are this big. No guarantee, but I would say not to study this. I don't think they ever, on any exam across all the professors at UTSA, I don't think any of them go above 10. So don't worry about it going above 10. All right, so now we're going to draw them. So first, our first step is going to be identifying our parent chain. So it's a decane, which means we have 10 carbons. So we have 1, 2. So remember 1 and 2. 3, 4, 5, 6, 7, 8, 9, 10. And now we figure it out, right? So we can pick a side. In this case, since we're not naming, we can just pick which side we want to start from. I like to think that drawing the molecule from the name is way easier, because in many ways it is. So I'm just going to write all of my methyls in green and all of my 1-tert-butyl in blue. So let's do all of our methanes. So I'm just going to start from this side. This is carbon 1. So we have methyl at carbon 2, and then 2 methyls at carbon 3, and finally our last methyl at carbon 4, tetramethyl. All right, so those are our methyls. And then at another carbon 4, we have tert-butyl. And that is a tert-butyl group. Because, let's draw it like this. 1, 2, 3, 4 carbons. That's where the butyl comes in. And then tert, because that's what it looks like, I guess. And here's the bond that connects it to the parent chain. So this is our molecule. And personally, what I would do, I would fix these bond angles like that. and that is that molecule. Let's go and see this one. We have methyl cyclopropane. So here's our parent chain, cyclopropane. Propane is a three carbon something, and it's cyclo, so it's a three-membered ring. That's a triangle. And methyl. So notice when we have only one substituent on a cyclic molecule, we don't put the number there because it doesn't matter. I could write one methyl, and technically it's redundant, right? Because if there's only one substituent, that is automatically carbon 1, no matter what. I could put it here, and it doesn't change anything. I could put it here, and it doesn't change anything. Because if I really wanted to, I could do the exact same thing by doing this. Oh, wow. See? So it doesn't matter. All right. This one, we have a hexane. Identify our chain, hexane. 1, 2, 3, 4, 5, 6. And let's see, let's do our methyls in green again, and this cyclobutyl in blue. So our methanes, I'm just going to pick a side. 1, 2, I'm just picking from the right side this time. 1, 2, 3. This one is carbon 3. 3 dimethyl, right? On carbon 3, we have 2 methyls, dimethyl. And on carbon 1, so same thing right here, we have a cyclobutyl. That's weird. So I've heard of cyclobutane. That looks like that. So all this is when a cyclo group, a cyclic I guess in this case, is acting as a substituent. So it looks like this. That is ugly. That is ugly too. That's better, I guess. So this is our molecule. So notice why is it not called, I don't know. I don't even know what it would be called. Something cyclobutane. Because it wouldn't be the longest chain, right? I can make a longer chain with this being my longest chain rather than the cyclic part, which is why that's a substituent. This is a substituent rather than it being the parent chain. All right, that's our naming. All right, guys, next we're going to be doing our Newman projections. So this one is kind of where things get a little bit, dizzy. But let's see. So we're going to draw the Newman projections for the following molecules from the point of view of the arrow. So we're looking down this part of the bond, right? We're looking down this way. So that means this carbon's in front and this carbon's in back. So let's go ahead and draw that. So I have, this is my front carbon, and then I'll have, let's see. Let's look at our dashes, wedges, and lines, right? So dashes, what does that mean? What does dashes mean? Dashes mean when we're drawing, it means it's going into the page. It's moving away from us. A wedge means it's moving out of the page. It's moving towards us. And if it's a line like this, it's in the same plane as the paper, right? It's in the line of the paper. So if we're looking down this way, down the bond, we see that this, you'll learn what it's called later, or do you know what it is? Yeah, hydroxyl group, this alcohol group is pointing down, right? So I'm going to draw my Newman projection with that pointing down. Like this. There's my OH. And then, right here, you don't see them, but I have some implied hydrogens here. So let's go ahead and draw those as well. I have one coming out of the page, and I have one coming into the page. So one thing to keep note, if you get confused, this part is out of the page, and this is into the page. Because if we look at this, if we're looking down the bond, this would be on our right side and this would be on our left side. Okay, and then to draw the back carbon, it's just a ring, in the middle. And we do the same thing. So we see that this ethyl group is also in the same line as our hydroxyl, so I'll just draw it right next to it, right? And you can either draw it in stick like this, which you can do that if it's simple, or you can draw it like this. So it's the exact same thing, they're not any different. And then we can draw that tert-butyl group. And how do we draw a tert-butyl group? Like this. Because we have that single carbon that has no hydrogens and 3 air quotes methyls coming off of it. Let's see if I can draw that a little. There you go. And then finally we have, it's not very clear, but if I take away my implied hydrogens, we have another methyl group that is going into the page. And this one I'll just draw as a stick. Or actually no, I have a theme going. There you go. And that is the Newman projection for that first one. Let's do the next one. We're going and looking in the opposite direction this time. So let's speed things up a little bit. We have our group that is in the plane going up, hydroxyl group, and then we have a NH2 coming out of the page, and we have a cyclohexane group. Like that. And that's that first front carbon. Then the back carbon, let's draw it. So this other cyclohexane group is in the page. So I'm just going to draw it kind of like, you know what, let's go from this side. All right. And then after that, we just have some implied hydrogens. All right, that's how you draw those Newman projections. All right, so our next step is going to be finding the most stable conformations for each molecule. So generally, that's going to be our staggered positions. So we're going to move this molecule in a way that the bulky groups are as far away as possible. Let's look at this first carbon here. And what is our bulkiest group? So we have hydrogens that are not very bulky, then we have a hydroxyl group. It's a pretty small substituent, but out of the 3, that's the biggest one. Now let's look at this back carbon. We have an ethyl, we have a tert-butyl, and we have a methyl. Which one is the biggest out of them? That's going to be this tert-butyl, right? So we're going to be trying to separate this tert-butyl from this hydroxyl as much as we can. So it's almost in that position. So all we got to do is just rotate this a little bit. So I'm just going to rotate it over just a little bit. And this time, since I have the space, I'll go ahead and just draw the substituents out. There we go. We had a methyl over here. We have an ethyl right there. That's our most stable conformation for that molecule. Let's take this one. And let's see. So what is our biggest substituents in the front carbon? It's going to be this cyclohexyl group, and in the back it's the same idea. The only other 2 are hydrogens. They're small. They're not going to be very sterically hindered. So we want to separate those cyclohexyl groups as much as we can. So let's go ahead and draw what that looks like. So again, what I'm going to do is I'm going to rotate this back carbon just a little bit that way. So that we can see. There we go. And that is the most stable conformation for those two molecules. All right, and now we're going to be drawing the least stable conformation. So I'm just going to go ahead and steal these. All right, so now to make the least stable, we're just going to be trying to get all of the bulky groups as close as we can. So pretty simply, all we would have to do in this case is take our bulky groups, bring them closer together. So I'm going to bring this all the way over, right? Big rotations. Basically, we're going 180 degrees. Doesn't matter which direction, I just made it negative. And we're going to try and get them as close as we can. And remember to keep the order, okay? That is the biggest thing that you might forget, is to not keep the order. So let's see here, that ethyl will go right here, and that methyl goes right there. And there you go. And what are the interactions between these bulky groups called? They're called sterics. And it's denoted like that. Let's do it for this one. This one's going to get crowded really fast. Alright, so that means I want these cyclohexane groups as close as I can. So rotating the entire molecule by 180 degrees. This one's pretty easy to keep track of because the only other substituents are all just hydrogens. So this is likely going to be a very sterically hindered molecule because we have those gigantic cyclohexane groups that are interacting with each other, causing a lot of steric strain. All right, and that's going to be our TA session for today. So thank you for listening in, and I'll see you guys later.